about how computers have evolved in last 50, 70 years, and we see that computers have become part of our life. It means that everything that we touch, maybe like everything, anything, has a computer built into it, which we can often not see, but as a computer engineer, you should be able to realize that the device has become intelligent. Say, for example, refrigerators. If you buy a refrigerator today, it has a built-in computer, right? Or if you buy a car, if you buy a high-end car, it will have more than 100 computers built into it, and including a Wi-Fi LAN and also actual wire LAN. Okay, if you buy, for example, uh, even a bulb, intelligent bulb you can get, which can be controlled with IP. Home security cameras, you can have, cameras which are internet connected over, in your house, so house can be made secure. In front of house, you will have locks that are all now internet. But apart from that, it has hundreds of other things. Okay, take for example entertainment. We used to go to movies, still go to movies, but very less in comparison to others. Now we have video on demand, right? Any movie you want to see, you can get it on Netflix or Amazon, whatever, Play or whatever. And similarly, TV channels. For example, I don't have Tata Sky or what or Airtel connection. Instead of that, I watch whatever TV I want to watch on my iPad. Okay. Um if you go step out of home, then you can see that everywhere you go, you will touch upon some aspect of computing. Say, for example, you go to movies, even movie tickets are available online, and then you are allowed to enter hall with somebody scanning your movie ticket, and that's all electronics. Yeah, so the computers have invaded our lives in every aspect, and what you can see, that's a great benefit for us because we have tremendous amount of productivity. At the same time, there are some disadvantages also because we are becoming less and less secure because anybody sitting anywhere in the world can invade into our devices. Okay? So today we'll see what has made this possible. And I'm sure you would have heard about Moore's law because in computing in the beginning itself, people, most of the lectures start with Moore's law. So we'll not spend too much of time, but we'll come directly to impact of that and what exactly is happening today. Okay, all right. So now we can say that world is becoming flat, or rather, world has become flat. You don't have to be in Silicon Valley to do fancy stuff, right? You can as well be sitting in a very small village in Madhya Pradesh called Gotegaon, and you can access any document, any artifact that anybody is sitting in Bay Area can do. You today, wherever you are in whatever part of the world, if you have internet and a computer, you are as good as that of any student in MIT or Berkeley or Stanford. Right? So you are not at a disadvantage uh, compared to students who are studying abroad. Okay, at the same, but that has not been the case for me about 30 years back, right? When I started my PhD, it took me 1 year to get the papers I wanted to have with me, right? Because I had to get some conference paper, journal papers, and these papers were available, not available in the place like IIT Delhi where I did my PhD, and I had to write a postcard to I didn't even have email, I mean, in the beginning. So I had to write a postcard or letter to the author to send the papers by surface mail. And surface mail means that the papers came 3 to 4 months after I had made a request by C post. C post essentially through C route. Okay. So that was a time. And now, if I have to do the same thing, then I can get all the papers that I have uh, within a day or so, right? Because once I have access to IEEE website, I can download whatever I want. And IEEE, by the way, has published the last 70, 80 years of papers into one CD. If I get that CD online, then I have access to everything. Or I don't need to do that today. I mean, actually, I just have login credentials and I get it. Okay. So what has made this possible? Today, why do you know where are the maximum number of jobs and where? I mean, I'm not talking about engineering itself, but anywhere. And what kind of jobs are earning maximum amount of revenue for the country? Any answer? Okay, it's nothing but IT. Okay, information technology or the services or the companies that we have here related to IT industry, that is the largest service provider in the country. Service provider in the sense that is generating the jobs in the country or job provider in the country, right? And India is earning maximum export revenue through it. What has that made possible that India could do so much while in other sectors we couldn't do? There are only two things. First thing is that computers have become cheap because when about 35 years back, 30 years back when I started my career, the whole IIT Roorkee or that time University of Roorkee had one computer, just one computer. Even faculty members didn't have PCs, right? And everyone went there and had just half an hour every day terminal time. It was so expensive. Okay, now none of you could complain that I don't have enough computing because your laptop is more powerful than supercomputer of that time. And that's one thing, right? I mean, so today on my desk, I have right now three computers, one iPad, my laptop, and two mobiles, which has at least 100 times more powerful than the what IT Roorkee had at that time. So affordable computing is one, then all of us can afford computing. It's available for free. Okay. And second thing that has happened, even when I started my job in industry in mid 90s, then we had satellite communication to connect to Hughes, where I have taken up a job, to their US center. There was no internet in, there was internet, but internet was not so much available. So people could connect through satellite communication to counterparts. And then since then, today, each one of us have tremendous amount of bandwidth available for almost like free. Okay. And there's a communication part, right? So now computing has advanced very fast from 1980s onwards or 1970s onwards. And then, however, the communication has not increased till almost like mid 90s. Okay, and after mid 90s, the communication has started since fiber optical cable have come and bandwidth has increased significantly. Cost per bit of transfer became very less. Then around mid 90s, you can see that jobs have started coming in India. Because I mean, once you have internet connectivity, it doesn't matter who's sitting in the next room. Next room could be as well in New York, right? Now you have same computing environment and you can sit anywhere and do the same amount, same work. Then it's just cost arbitrage, where the salaries are low and people can do good jobs will move there. So India has tremendous potential now in IT industry. And and that's the reason we see in Bangalore every nook and corner, whatever Silicon Valley companies are there, they're available here as well. Right? So there's a background. And so computer technology has progressed very, very fast in last years, and because of What? Because the processors have become very, very powerful. Every year and a half and 2 years, the power of processor doubled. It means that integrated circuit became denser and denser. More transistor we can pack in into same area. The number of transistors that could pack into the same area were doubling every 2 years. It means that computing power was doubling every 2 years. Okay, and other way of looking at it is that if I have X amount of computing, every 2 years the cost is reducing by half. Okay, keep the cost same, then we can say that keep power of the processor is doubling. And similarly, memory have improved, right? So when I say computer, it's not only CPU but also memory and associated things. Okay, so communication lagged behind 30 years. Now it has caught up. Okay, all right. So let's move on to now Moore's law. Moore was a founder of Intel. Okay, and then he looked at the how things are changing because they were one of the top companies in semiconductor area, and they could see that he could visualize is that number of transistor on chip will double every 18 to 24 months. Okay, and this law, it means that semiconductor technology will improve continuously, right? New technology comes that you can put in more transistors per square centimeter. Okay? So, and this has remained true for almost like 50 plus years and still true. Now people say that's almost flattening now, linearly increasing. It's actually linear curve. So that's the beauty, right? And so it means the cost is reducing simultaneously by that much. We can see the graph here. Okay, and what we have already discussed, transistors are becoming smaller and smaller. There is kind of 70% dimension reduction, or sorry, every new generation is reducing it by by 30%. Okay, so now transistor dimension is between 5 nanometer to 20 nanometer. Like transistor count is increasing as per Moore's law. Okay, and a microprocessor today can contain almost like 10 billion to 60 billion transistors. And there are three processors that I have named here. The one at the top is Apple A14X, which is 5 nanometer, which has 15 billion transistors. NVIDIA's processor, which they make GPU, graphics processors. I mean, normally now we have a main processor and also attached processors, right? So graphics processor is designed to do graphics operations. Uh, okay, so that has 54 billion transistors. It's a 7 nanometer. And then not processor, but we also have a DRAM chipset by Samsung, which has capacity is 8 terabit and which has 2048 billion transistors. Okay, so it means that Moore's law is still applicable, and a number of transistors are still increasing linearly. But we can see some trend here, right? And there are some constraints now being posed. So we can see in this graph that there has been linear increase, okay, and in terms of number of you know number of transistors and also the performance. But we can see that now it's slightly flattening out, although increase is still there. Okay, so earlier increase was 52% per year. Now increase is almost like 22% per year. Okay, because more transistors are still being packed into a chip, but at the same time the degree, I mean the improvement is reduced. Now the constraints are coming because of other things, right? So earlier, as we were, you can see that as the integration is increasing and number of transistors increasing, now here this Y dimension shows performance, and performance, of course, because of more transistors are doing work in a chip. But at the same time, we can see the clock speed is also increasing, right? The clock speed here is 500 megahertz, and now we have around 3 or 4 gigahertz. Okay. Now, beyond this, we are not able to increase the clock speed. Okay. Now, of course, you know why clocks are used, right? Within a clock period, certain amount of work is done. Okay, and clock edges we use for transition. So if and an instruction, machine level instruction can take multiple CPU cycles or clock cycles. Okay, so if we increase number of clock cycles, then of course our program will take uh, less time because clock period is reduced. Okay, so now there is always a limit now. Okay, how much clock speed we can increase, and then this limit in terms of now this limit in terms of the performance we can achieve on a single processor is that that limit is because of the power. Now this power here, power is electrical power. Okay, and then instruction level parallelism, how much work we can do within an instruction. Suppose we have instruction something like this, adding two integers. Now can part of this be done parallelly? Okay, so that's we call it instruction level parallelism. Okay, and then memory latency, how much time we will take to read something from memory. But the biggest constraint, of course, this cannot be, the second one cannot be changed too much because it depends on the way your ISA or instruction set architecture works. But the power is something that's interesting, right? Why? What is the constraint of power? Now, we can say that for a for a processor, maximum we can tolerate is about 250 watt of power, or 250, 200, 250, sometimes 300. That's the limit. Now, this constraint is not coming because of anything but because of the heat it generates, right? Now, beyond this, if heat is generated, then it cannot be cooled. Okay. So now power is causing the biggest constraint. Okay, if more number of transistors are there, and a transistor in general, a MOSFET or basic transistor will have capacitance for charging and discharging, right? And capacitance requires some power to charge, right? And more the power, more the number of transistors, more the power that will be there, and more the heat. Okay, so now we have considered the power which is around 200 to 50 watts. Then we have to devise methodologies such that we can utilize more number of transistor per chip.